We'll see the next question. Consider the common collector amplifier in the figure. Bias circuitry ensures that the transistor operates in forward active region, but has been omitted for simplicity. Let collector current IC and VBE be the base emitter voltage, VT be the thermal voltage, and GM is the transconductance, R0 is the output impedance. Which one of the following conditions ensure a nearly constant small signal voltage gain for the wide range of RE emitter resistance? If you observe carefully, the given circuit is like this. This is the transistor. Input is given at the base. This is the input voltage, and output is collected across the emitter resistor. This is emitter resistor RE. Output is taken here. So by observing this circuit, we can say this is a common collector configuration, CC configuration. So if you draw the equivalent circuit for this, like the video, share the video, and subscribe to the channel for better content and more videos. You will get the current source here. This is the collector current that is flowing, and there will be emitter model resistor RE dash, which is very small resistance. And here the input voltage base terminal will come. This is base terminal. This is the input voltage, and in series with the emitter model resistance, there is capital RE, that is emitter resistance. Okay, output is collected across the emitter resistance. So this is basically VBE. This particular voltage is VBE, base emitter voltage, that is the voltage drop across the emitter model resistance. Now, if you see, this is the collector current IC, which can also be written as beta into IB. So now, this collector current IC, which is equals to beta into IB, can also be written as GM transconductance multiplied by VBE. Okay. How it can be written? Because the reciprocal of a transconductance is nothing but impedance. So voltage by impedance is nothing but current again. Okay. Hope you understood this. So now here the condition is the collector current is far greater than base current. So you can write this as transconductance GM VBE is greater than IB, because the collector current IC can also be written as GM into VBE. So now voltage gain, if you see, the voltage gain AV is equals to output voltage divided by input voltage, which can also be written as output voltage is nothing but output current multiplied by output resistance, that is RE. Here the collector current and emitter current both are same. So I am writing IC is approximately equal to IA. So I am writing IC into RE. The output voltage is collected across the emitter resistance divided by input voltage. Input voltage is, if you apply the Kirchhoff voltage law in this particular loop, input voltage is VBE plus V naught output, V output. So input voltage is VBE plus V output. So AV voltage gain is equals to GM VBE dot emitter resistance RE divided by VBE plus V output is nothing but again GM dot emitter resistance dot VBE. So if you take out VBE and cancel it, you will get GM transconductance multiplied by emitter resistance 1 plus GM RE. The value of GM multiplied by transconductance and emitter resistance is far greater than 1. So voltage gain can be approximately made equal to 1. So now here is the trick. So GM can be written as the collector current divided by VT, thermal equivalent voltage, emitter resistance greater than 1. This you can write as IC multiplied by RE greater than VT. So this is the equation we derived from this. So now from the given options, the right answer is option B. We'll see the next question. If the emitter resistance in a common emitter voltage amplifier is not bypassed, what will happen? So we'll see the two conditions here. We'll draw the diagram. This is the collector current. This is the transistor. This is the emitter resistance. Here we have got two resistances, emitter model resistance, which is very small resistance, and emitter resistance. This is the base where input is given. Okay. So here the common emitter he told, so output is collected at the collector. This is without bypassing. With bypassing we'll see. There is again a collector resistance, transistor, output is collected across the collector. This is the base where input is given. There is a emitter model resistance. There is emitter resistance, and this emitter resistance is bypassed. Okay. In these two cases, we'll try to derive the input impedance and voltage gain. So if you see here, the input impedance will be, if you apply the Kirchhoff voltage law, the input impedance you will get as beta times Re dash plus 1 plus beta into capital Re. This is the input impedance. Whereas the voltage gain AV is equals to output voltage divided by input voltage. The output voltage is nothing but collector current multiplied by load resistance, that is collector resistance, divided by input voltage is nothing but input current IB multiplied by input impedance beta Re dash plus 1 plus beta capital Re. So this IC by IB, you can write this as a current gain, the collector current divided by base current, you can write it as current gain AI. So this is the voltage gain here. In second case where emitter capacitor is there, here the input impedance is beta Re dash. There will not be 1 plus beta Re factor because the emitter resistance is bypassed. The emitter capacitor acts like a short circuit in the AC load line analysis. So now here the voltage gain also is equals to AI RC divided by beta into Re dash. So by comparing these two formulas, you can tell that by removing the emitter capacitor, if the question is if the emitter resistance in the common emitter voltage amplifier is not bypassed, means if you remove the emitter capacitor, what will happen? Voltage gain here will reduce, input impedance will increase. It will reduce the voltage gain and increase the input impedance. So answer is option B. Like the video, share the video, and subscribe to the channel for better content and more videos. We'll see the next question. In the circuit shown, the silicon BJT has beta is equals to 50, VBE is 0.7 volts, VC saturation is 0.2 volts. Which one of the following statements is correct? Actually, here the statements are like this. Option A, for collector resistance RC is equals to 1 kilo ohm, transistor operates in a saturation region. BJT operates in saturation region. This is the first option. Option B is for collector resistance RC is equals to 3 kilo ohms. BJT operates in saturation. BJT operates in saturation. Let's take these two options and try to solve the question. So now, if you observe, what is the collector resistance value that suits to drive the BJT into saturation? That is the question now. We'll see. If you apply the Kirchhoff voltage law in the input loop by applying KVL at the input loop, you will get VBB is equals to IB into RB plus VBE, base emitter voltage. So here VBB is 5 volts. The base current is not known. Base resistance is 50 kilo ohms. Base emitter voltage is 0.7 volts. So the base current is equals to 0.086 milliamperes. This is the base current. And here the collector current IC is equals to beta into IB. Beta value is given as 50 and the base current is 0.086 milliamps. So the collector current is equals to 4.3 milliamps. This is the operating collector current we got. The condition for a BJT to be in saturation is the flowing collector current. The current flowing collector current must be greater than saturation collector current. Okay, or the flowing base current must be greater than base saturation current. How to find out this saturation current? The flowing collector current is known for us, that is 4.3 milliamps now. Okay, the collector saturation current is nothing but VCC minus VC saturation divided by RC. This is the collector saturation current. You have to calculate. This flowing collector current we have already calculated here. Okay. Similarly, the IB saturation. How to find out IB saturation? IB saturation is nothing but IC saturation divided by beta. This is the way how to calculate. Now we'll calculate IC saturation. IC saturation formula we have given here. This is the formula. VCC minus VCE saturation divided by RC. So here two collector resistances are given. RC1 and RC2 we'll see. Okay. If here two collector resistances are given, so we'll calculate two values. For RC is equals to 1 kilo ohm. What will be the answer? So VCC is 10. VC saturation is given as 0.2 milliamps divided by RC 1 kilo ohm. What will be the answer? This is 9.8 milliamps. And similarly, for RC is equals to 3 kilo ohms. 10 minus 0.2 divided by 3 kilo ohms. This will be 3.266 milliamps. If you observe, this 9.8 milliamps is greater than 4.3 milliamps here, and this 3.266 is less than 4.3. So for the transistor to operate in a saturation region, the resistance RC value must be equal to 1 kilo ohm. So the answer is option A.
Let's see one more question. The L-bus model of the BJT is valid for. First, what is the L-bus model? We'll see. Okay. This is the PNP transistor. This is the PNP transistor, P, N, and P. You can write this PNP transistor like this. This is the emitter, base, and collector. The L-bus model will be drawn in the form of diodes. This is one diode, and this is another diode. This is the emitter, collector, and base. But we need to write the current components also. There are 4 current components. This is the forward current IF. These current components are very important. As the diode is facing this side, there will be a current component in this direction also, that is called a reverse current component IR. And this forward current gets amplified and projects out at the collector. That amplified current factor is this. This is alpha FIF. Similarly, this reverse current also gets amplified and projects out of the emitter. This current component is alpha R IR. These are the 4 components that we have. Okay. Based on the biasing conditions, these 4 components gets activated. How does it work? You just see. This is the base emitter junction, diode E, emitter diode. This is the collector diode. Okay. Collector base junction. Now, based on the biasing conditions, there are 4 types of biasing conditions that we have for the transistor. Okay. Operation mode, if you see, operation mode, input junction, output junction, and currents that get activated. We'll see this. So if the operation mode is if the operation mode is saturation region, if the transistor is working in saturation region, both junction, input emitter junction and output collector junction, both should be forward biased. And the currents that will be activated will be IF and IR. Both currents get activated, IF and IR. Similarly, for the active region, input junction is forward biased and output junction is reverse biased. So the currents that get activated will be IF and alpha IF. These two currents get activated. For the
Cutoff region, if you see, in the cutoff region, both input junction and output junction both will be reverse biased. So which currents will get activated? Alpha IR, and alpha IF. These two currents will get activated. In the fourth region, that is inverse active region. Inverse active region. In the inverse active region, input junction is reverse biased and output junction is forward biased. So here, which currents will get activated? It will be alpha IR, and capital IR. These two currents get activated. So if you see, overall, the Elbers model of the BJT is valid for all the regions: saturation, active, cutoff, and inverse active. So answer is option D.
we'll see the next question.
Like the video, share the video, and subscribe to the channel for better content and more videos.
An increase in the base recombination of a BJT increases. So the base recombination, usually base recombination increases when the base width increase. When the base width increases, base recombination will definitely increase. Means base current will increase. Second case is when base doping concentration increases. Base doping concentration increases. In either of these two cases, IB increases. So the total current, emitter current, is given with the base current plus collector current. So if IB increases, IC automatically reduces. Okay, so IE remains constant. The emitter current is a constant parameter here. Okay, so if you see the first option, common emitter DC current gain will increase hastily. If IB increases, IC reduces. So beta is IC by IB. So this will also reduce. So option A is wrong. Second option is the breakdown voltage of BCE naught increases hastily. So if you see the power rating of a transistor is given as B VCE naught multiplied by ICE naught, which is a constant. Power rating is a constant parameter. Here what happens is, if you observe carefully, as IB increases, IC naught, the reverse saturation current, decreases. If IC naught decreases, ICE naught is equals to 1 plus beta IC naught. If IC naught reduces, ICE naught also reduces. So when ICE naught reduces, the breakdown voltage should increase because the power rating is a constant parameter. If one parameter reduces, the other parameter should increase. So there will be an increase in the breakdown voltage. So option B is right. Similarly, if you see third option is unity gain cutoff frequency, that is FT. FT is equals to GM divided by 2 pi C pi plus C mu. These are the capacitances, inter-electrode capacitances. These capacitances are the constants, but GM can be written as IC by BT. So here collector current already reduces. So this also reduces the FT also. So there is no scope for unity gain cutoff frequency to increase. So this is also wrong option. Next comes transconductance. Transconductance we have already seen, IC by BT. So if IC reduces, transconductance also reduces. So this is also wrong. Answer is option B. We'll see the next question. A good current buffer has low input impedance and low output impedance, low input impedance and high output impedance, high input impedance and low output impedance, high input impedance and high output impedance. So good current buffer. What is a current buffer? Current buffer means the device which gives the current gain as 1. Approximately it should be 1. That is called current buffer. The best example for this is the common base. Common base amplifier. If you see the common base amplifier, this is the emitter, this is the NPN transistor, this is the collector, output junction is reverse biased, input junction is forward biased. Okay, the input current is the emitter current, the output current is the collector current. The input current is the emitter current, output current is the collector current. Okay, here the input current, emitter current, is equals to base current plus collector current. As the base current is negligible, the emitter current is approximately equal to collector current. So the gain, if you see alpha, the output current alpha IC divided by IE is approximately equal to 1. This is the current buffer device. It gives the voltage amplification. The voltage amplification will be around 150, but the current amplification is 1. This is the best example of current buffer. So for this, if you observe carefully, as the input junction is forward biased, the input impedance is very, very low. Input impedance for current buffer device will be very, very low. Whereas the output impedance, as it is reverse biased, the output impedance is very high. The output impedance is high. So answer is option B, low input impedance and high output impedance. Similarly, if he asks for voltage buffer, for voltage buffer, what is the answer? Reverse. For voltage buffer. For voltage buffer means the device which offers voltage gain is equals to 1 and current gain will be there. This is the example for this is CC, common collector amplifier. Input impedance is high. Input impedance is high. Output impedance is very less. Very low. Okay, like this you should understand.
Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.